Let's do some problems from the Mira Costa pre-calc first semester exam review guide. It's about, I think it's 16 pages and like 180 something problems, chapters 1 through 5. This first section is about piecewise functions, and it's asking about continuity. Piecewise functions have multiple segments. If you think of it graphically, it goes something like that. Maybe there's an open dot. And these two different segments, these different legs, can be joined or disjointed. So this one, as I've drawn it, there's a discontinuity, but sometimes the two legs, join up, which would make it continuous. So when we're looking at the function written in this format, this tells you where this function applies, and this tells you where the other function applies. So if this is going to have a discontinuity, it's going to happen where the switchover occurs, or where the domain changes from one function to the other. Basically, you just plug in whatever number is in common between the two functions. You plug those numbers in to both functions separately. If the output matches, then it's continuous. If it doesn't match, the opposite. So let's plug in 0 to this function. We get 0 plus 0 minus 4. So we get minus 4 as our output. And this one we get minus 5. So that's a discontinuity. They don't match. So at 0, it's a discontinuity. So where is it continuous? From negative infinity all the way up to 0. And then there's a break, then 0 to infinity. So this one, number 2, same thing. We're just going to plug in 3. Just the boundary between the two segments as an x value into each function. So here we get 6 minus 3 is our output is 3. We plug in 3 and we get 9 and 9 and negative 18. So that one is 0. So it doesn't match up, so it's a discontinuity. So not at this 3, but as at x equals 3, there's discontinuity. If it was continuous, if these numbers matched, there'd be no break between the segments, right? There would be something more shaped like this. If that was the case, it would be continuous over the entire domain, negative infinity to infinity. But there's a break. So it's only continuous from negative infinity all the way up to 3. And then it resumes being continuous from 3 to infinity. So in my opinion, this is the right answer. So you notice the difference is I have open brackets. And you might argue and say, yeah, but this should be a closed bracket because it's less than or equal to. I guess that would be true for like where the function is defined, but at 3, even though it's a closed dot, it's not continuous at 3. It's not like continuous on this side, but discontinuous on this side. So in my opinion, A and B are both wrong. It should be like this. But I guess if you have to go with what's written there, this one does have the or equal to, so I guess you'd go with A, the closed bracket. Number 3, we plug in 0 into both functions. We get 1 as an output, and we get 5 as an output. So definitely a discontinuity at 0. So we're going to go negative infinity all the way up to 0. And then 0 to infinity. All right, see open brackets again. And number 4, use graphing calculator to find relative extrema. So let's do number 4 first. We're just going to type that into our TI-84. And then we'll graph it. And I guess we could zoom in on that little section, but I can see that there's a max on the left and a min on the right. But we're just going to go second calc. Let's do minimum. We'll just put our left bound, right bound. So just click 1 to the left. We'll write that down. Our minimum is 3.66 and 3.85. 3.85. And then just repeat second calc maximum. And same thing, left bound, right bound. So 3,4. So I guess to be safe, maybe I would write, which one was the max, which one was the min next to it. We said this one was a min, but yeah, this one was a min, a relative min and a relative max. And then you would just repeat that same process for these ones. I don't think anything's going to be different, so I'm just going to skip those ones. All right, let me type this in. Use this button, the fraction button right here, alpha, and this thing. And I see it has a segment of decreasing, then increasing, then decreasing. And the boundaries between those will be the maxes and the min. So second calc min, left bound, right bound. Okay, so the very minimum occurs at x equals -2. So I know this function is decreasing from all the way from negative infinity all the way up until -2. And should it be closed bracket or open bracket? It should be open bracket for increasing, decreasing. It's always open bracket no matter what. Let's see. And that maximum will be also at +2, because I did this problem already, I know, but normally you'd have to do second calc maximum and find that maximum point. But I already did it, so it's decreasing from -infinity to -2, and then also from 2 to infinity. And it's increasing from -2 to 2. All right, domain and range, intercepts and behavior. Domain and range for this one. Let's see, for this one, domain is -infinity to infinity, and range is 0 to infinity. The x-intercept is 0, 0, and the y-intercept is 0, 0. And the end behavior, you write it like this. X goes to -infinity, that's the left side. Y goes to infinity, which means it's going up. And this arrow, you'd say it's on the right side. So as x goes to +infinity, y goes up to infinity. Let's see, this one, domain and range, again, domain is all reals. Range is also all reals. X-intercept 0, 0. Y-intercept 0, 0. Sometimes you'd say the x-intercept occurs at x equals 0, y-intercept at y equals 0. You could say it either way, but I think that's more correct. End behavior, let's see on the left side. On the left side, as x goes to -infinity, y goes to +infinity. As x goes to +infinity, meaning the right side, y is going to +infinity. And whoops, I made a mistake. On the left side, as x goes to -infinity that way, y is actually going down to -infinity. There we go. So this one, pretty much the same thing. Domain is -infinity to positive. The range is, let me go back and check that last one. The range is closed bracket 0 to infinity, open bracket. The x and y intercepts are both 0, 0. As x goes to negative infinity, y goes to positive infinity. As x goes to positive infinity, y goes to infinity. Let me go check that last one. Yeah, didn't put a closed bracket for the range. Right, this one should be closed bracket. 13. Average rate of change over this interval. So these are both x values, x1, x2. And the average rate of change, all it is the slope. So we have x1 and x2. We just need to plug in x1 to get y1. Let's see, plug in -2, we get +4, we get 8 minus 4 minus 1. So that's 4. This one is 3. -2, 3. On this thing, oh man, fractions. So let's see. I have to write that out. So this will be +25/9 minus 10/6, 10/3. It's 1. Yeah. Right. So 15/9. And then this one I need a common denominator, so multiply top and bottom by 3. Guess I need a common denominator there. So 9/9. All right, 50 minus 30 is 20. Minus 9 is 11. And then when I plug it into the slope equation, let's see, it's y2 fractions minus y1, 3, x2 minus 2, so plus 2. And to solve this, I need to get a common denominator, top and bottom. So let's see, 3/1 is going to be 18/9. Multiply top and bottom by 9. Okay. 27. And this one, yeah, I could go for a denominator of 3 or 9. I guess I'll just keep it as 3. So, what's that? 11 minus 27, same as 27 minus 11. So, 16. This one, 3. And then keep change flip. So those cancel. And I get -16/3 is the average rate of change. So for me, just to check that, I kind of know, like we're done. That's the answer. But I'm just going to do a sanity check. The graph of this, which kind of looks like it's a parabola, it's upward facing. It's got a y-intercept of -1. We get 2 into it. So it looks something like that, or maybe it's like that. Let's see, -2, 3, and negative, I don't know, 9. Yeah, my points don't seem to agree with that. Let's see, -2, 3, -5/3, 11/9. Those are both up here. So how's it going to get to -1? So I guess it could be like that, maybe. I guess my sanity check, it's too coarse. I'd have to like maybe plug this in the calculator, get a more realistic view of what the graph looks like. But I'll say, yeah, it looks good enough. You can skip that part. I'm on 16. Looks like we're doing some transformations. So let's see. So this one, we've got a number inside the function and a number outside the function. It's a negative. So let's see, this one is going to be a vertical flip. It's negative. I know it's vertical because it's outside. And this one is a horizontal, looks like a shrink, but because it's horizontal, it's the opposite. That one's a horizontal stretch by a factor of 3. And this one, it's a vertical flip, but they like to say it's a reflection across the x-axis. Same thing, it's flipping it upside down. Here's a quick summary, partial summary of some different types of transformations. I'm just using the parent function y equals x squared, and I'm placing a 2 in different locations. Each of these 4 squares has a variation. So let's see, in this one, I put a multiplier outside the function. It's outside the squared. So that's a vertical stretch by a factor of 2. This one, I put the 2 inside the function, in there with the x, which means it's a horizontal stretch or a shrink. Yeah, it looks like a stretch of 2, but the horizontal stuff is the opposite of what you think it would be. It's a horizontal shrink or compression by a factor of 1/2. This one, the 2 is added and it's outside, so it's a vertical, and because it's added, it's a shift. Outside is vertical, multiply is stretch, added is shift. This one's outside and added, it's a vertical shift up 2. Inside is horizontal, added is shift, so this one is left 2. The thing that's left out of this is the flips. This was a -2, this would be a vertical flip. But they like to say a reflection across the x-axis. If this one was a negative, it'd be a horizontal flip or a reflection across the y-axis. All right. So, quick review of transformations. All right, this one, primary function is root x. Let's see, I've got a horizontal flip, but they like to say reflection across the x-axis, across the y-axis. Across y-axis. And this one, I gotta be careful. Is this outside or inside? If it was like that, it'd be inside, but it's outside. So this one is vertical and it's added or subtracted, so it's down by -1, or down 1. Here I've got a negative outside, so that's a reflection, a vertical flip or a reflection across x-axis. It's got a 3 on the inside, so it's a horizontal compression or shrink by factor, can't say 3, you have to say a factor of 1/3 for shrinking. All right, back to piecewise. I think there is a way to do this in your calculator. Maybe I'll try to remember that next. But this is a rational function. For those, at some point you learned like how to find horizontal asymptotes, vertical asymptotes, x-intercepts. I'll start by, it's clear there's a vertical asymptote at 3. So maybe I'll graph that. And then a horizontal one at 0. And then I would plug in some numbers, but it would look like this, whole graph. But this one only applies to the left of 2, so I'm going to erase all this part. It's just going to stop right here. I guess I'm going to have to plug in the actual number 2. Let's see, 1 over -1. So it's actually at 2, it goes to -1. So right there, and it should be an open dot. So I'm just going to keep this part of the graph. I previously went down there. All right, and here's another rational function. This one has a asymptote at 0. Y equals 0. Just this one would look like this. And I won't even draw this part. Maybe it will look like that, but I only need to keep it to the right of 2. So let's see, I'm going to actually need the actual y value at 2. So let me plug in 2. I get -2. Okay, I guess I'm upside down. So it should be right there. So yeah, with that negative, the graph would have been like that. I only need to keep to the right of 2, so I'll delete that. There's my final graph. Right, do one more. All right, I did it on the graphing calculator. Let's see on this thing. It's kind of a pain. Doesn't work that good. So this is how you enter a domain restriction. You type in the equation. I guess you have to put in parentheses, supposedly. And then this is the domain in a second set of parentheses. No comma between them, just parentheses. And to get that inequality symbol, it's under second test. You can scroll down and grab it. But this is the graph. It's not perfect. It gives you these extra lines, like the lines at 0. So this red line at 0 shouldn't be there, and the blue line at 0 shouldn't be there. The graph is just this part. Bam, bam. Probably not worth it to use the calculator unless you're really, really desperate. All right, so number 20, I guess we'll knock that one out real quick. I'll try that one in the calculator too. So let's see, to get the absolute value, let me delete this. I need my parentheses. So I want absolute value in the x. That's under maths. Yep. Just 2. X is less than or equal to 1. I guess I'm not going to worry about the less than or equal. I'll just make it -1. Let me move this over. I'm on number 20. This thing, -1. I think I used the little negative. There's my parentheses. Yeah, way better if you just know what the graph looks like. This is super annoying. Oh my god, so annoying. Second, insert 2. All right, let's look right. Yeah, greater than equal, it doesn't matter. Okay, so it's just gonna be that segment and this one. So let's see. So it looks like, just guessing, it goes to 1/2. Maybe I'd want some accurate points here, or I could just fake it. Let's see, this one, that one's pretty clear. It goes to -2. Let's see, something that might help me with this is to go format and then grid, put the grid on. I like the dots. And that might help me locate some of these points. I think, let's see if I go -2, 1, that looks like a point. So I'd come back to my graph, go -2, 1. Let's see, -4, 2. So I could grab some accurate points. All right, let's go to the next one. Yeah, see, it's a transformation. Just flips upside down. And then I just keep the part to the left of 4. So it should look like that. Let's close dot. And the right side is a right side up one. Just keep it to the right of 4, so it'll be that part. And then I guess I wasn't careful with the other ones. This one should be an open dot. Let me go back to the other one, make sure I was careful with that. Nope. So this right side should have been an open dot. That one I've got the open dot. Okay, so this is another way of writing f of -3 times g of -3. So in this case, all I have to do is plug in -3 into that one, and then plug -3 into that one, and then multiply the two results. So you get -4 and -2. So that times that is +8. These are pretty smooth. Let's check that one. So the same thing, it's h of -1 times g of -1. So I'll plug it in there. Let's see. -4. Trying to be careful. +3 minus 1, 2, so I get -8. If I was taking the test, I'd be more careful here. I'm trying to rush and be quick, but I'm being a little careless with the negatives. But so you better double check all that stuff. I'm not that worried about getting it all 100% correct. Okay, so this one, same thing. I'm plugging in -7 into both. In this case, I'm just adding both results. So same and divide, but 25 is different. It's not times, it's an open dot, it's of. So it's the same as h. All right, h of g of -6. So for this one, I'll work from the inside out. I plug in -6 into g, and that'll give me, turn this into a number. So let's see, 36, +36 minus 1 is 35. So this becomes h of 35. Then I plug in 35 into this one, 76. Number 28, inverse, which means we switch x and y, then solve for y. So I switched x and y, then just solve for y. Multiply both sides by 3, because I'm going to get rid of that denominator. Yeah. Some teachers are sticklers. You maybe should write that last step, making y on the left side. So 29. Just switch them to finish it off. I guess maybe I should put n there. N is x in this case. All right. Tricky, what do you do here? But usually whatever the denominator is, you'll multiply it. Some kids will want to do put a 1 under the n so they can cross multiply. I'm just going to multiply both sides by that denominator, and it's just going to appear on the left side. I need to distribute. trying to get that y by itself. And then last step is just to divide by negative n. So it's right there. A new topic. Let's see, chapter 2. So this is polynomials, and I see some of that language, zeros and turns and intercepts. Got this function. It's a 4th degree. So I know it's going to have 3 humps, or you might say 4 directions. Yeah, I guess this is a 1st degree. This is a 2nd degree, which we're familiar with. So I think y is x squared. 3rd degree looks like that. Right, 2 humps or 3 directions. And a 4th degree, it looked like that. And so on. So the maximum number of turns for a 4th degree is 3. It doesn't necessarily have to have 3. It could have 1. So whatever the maximum number is, if you subtract 2, you get another possible variation. This would be just y equals x to the 4th, which would just have 1 change in direction. This one's got, let's see, 2 changes in direction, but if you subtract 2 from that, it would have just 1 change in direction, or 0 change in direction. This would be y equals x to the 3rd, no changes in direction. This one, let's see. I think I messed up there. This one has 2 changes in direction, so if you subtract 2, it's 0. This one has 1 change in direction, so you can't subtract 2. You can't have negative 1 change in direction. So, okay, at most, what did I say? 3 changes in direction. So that's the answer to 1, 3 changes. They didn't ask for all the possible changes, but if that was the question, you'd say 3 or 1 change. To determine the real zeros. For that, you have to factor this. I think you get your calculator on your test, so you could just punch this into the calculator. My graph came out like that. And I can see the zeros are at, I guess you can't see my cursor, but let's see if I can change that. Nope, can't see cursor, but I can see it's crossing at x equals -3 and -1 and 0. So I can tell from the graph that my zeros are, let's see, -3, -1, and 0. And 0 is a multiplicity to 0. I can tell from the graph. So it bounces off the x-axis. All right, if you didn't have the graphing calculator, you have to factor this thing. I see it's got a GCF of x squared. So I'll pull out a -x squared. Left hand side is plus 4x plus 3. And then this factors pretty easily into x plus 3 and x plus 1. All right. So the zeros are 0, and there's 2 of those. That's a multiplicity of 2, and then -3, -1. X-intercepts, which are basically these same points where the graph crosses the x-axis, or does not cross the, wait, what's the x-intercepts where the graph crosses the x-axis, and those where it does not cross? So I guess what they mean is this one, it doesn't actually cross the x-axis. So we're going to say x equals -3 and -1 are x-intercepts that cross. X equals 0 is an x-intercept that doesn't cross. Describe the end behavior. So the the negative on any of these functions will tell you that it goes down to the right. So our end behavior, we're going to say as x goes to infinity, y coordinate goes to negative infinity, just solely based on that leading coefficient being negative. And then to work out the left side, it'll depend on the degree of this. If it's even, it'll go the same direction. So ours is even, so it will also go down. So we'll say as x goes to negative infinity, y goes to also negative infinity. But if it's odd, like a 3 or a 5, it will go the opposite direction. Let's try one more. So looking at 33. Okay. So this one's not so easy to factor. So if I had my calculator, I would definitely just use my calculator for this one. Too many directions. All right. I don't know if it said calculator aloud, but I think you get your calculator on your test. So graph that up. All right, I graph it and I got this. So guess I should zoom out and make sure it's not bigger. So yeah, I'll do that real quick. Window. There we go. So I'll just go really big. I'll say 100. Just to make sure. All right, so I'm pretty confident it just has that 1 0. Which I should have written down what that was. Oh, I'm just going to zoom standard to get me back. All right, looks like it's at 1, so it's just, I guess the factored version of this function would be just x minus 1 must be multiplicity 4. Okay, so I'll just graph that. I should probably do the y-intercepts more carefully. So for that, I would plug in 0, 0, 0 for x, and it looks like it'd get negative 1, so it looks pretty good. Let's see. The end behavior, because it's negative, it goes down on the right, and because it's even, it's going to do the same thing on the left side. Listing all the zeros are just 1, and there's 4 of them there. And it only has one x-intercept, which does not cross the x-axis. All right, let's jump to a different kind of problem. All right, we got some polynomial division problems. Looks like we can use the synthetic for all of these, luckily. Let's see, different formats, different teachers, but I'll just go with this one. Don't forget to switch the sign. And let me check for any missing degrees. 4, 3, 2, 1. It's not missing any. 3, negative 20, 7, negative 12, and 13. So it's bring down, then multiply and add. Multiply, add, multiply, add, multiply, add. We get a remainder of 3. So it's in fraction form. Okay. That's random. All right, so this is 1 degree less than the original problem. So this is 3x to the third minus 5x squared plus 2x minus 2 with the remainder of 3, which we'll write as 3 over x minus 5. I guess that's what they mean by fraction form. Let's leave it. And I'm just going to erase that. Skip to 37. So 37, I guess, yeah, you can just plug in negative 2. But the other option is to use synthetic again. It's probably easier just to plug in the 2, but this is the second option. Bring down, multiply. add, multiply. And so the answer should come out to be -10 if we plug in -2. That's the remainder theorem. Don't know if you guys did that. Well, let's just do it the old-fashioned way. So we plug in -2, we get, let's see, -64. And here we get +64. And here we get +20. So I guess the answer is 20. Let me check my math over here. Yeah, all right, let me pause and check that. I wonder if was I supposed to change that sign? No, it doesn't sound right. -2, 8, 16. I guess I forgot. Oh, I forgot the last number. There's supposed to be a 0 there. That's what it was. Tricky. Yeah, 3, 2, 1. I have to have a constant. Okay, so bring that down and multiply 20. There we go. So forget that. I'm not doing that again. I'm just going to plug in the number. Okay, yeah, this is correct. These are x plus 5 to the third power. Okay, write a polynomial with these with these zeros. So it's going to be x minus 3/4, so plus 3/4, and then x minus all right, so for this one, I guess most kids are just going to like distribute the negative. I think I'll start off like that. No, I won't. I'll use, there's a trick to this. But yeah, you have to start off by distributing the negative. That's x minus 1 minus 5, x minus 1 plus √5. And then what you do is you come in with some parentheses, you put them like that. And you treat this as conjugates, where this is the first term, that's the second term, and this is the two different signs. So in conjugates, you only have to do the first term times the first term, and then subtract the last term times the last term. Or you could just do like that super distribution if you don't want to use the shortcut, which would be, you know, distribute the x, distribute the 1, then come back and distribute the -5. And it'll give you 9 terms. You'll have to find the like terms, add them up. But I'm going to use the shortcut. So let's see, it's x minus 1 squared, and then minus √5 times √5. And this is x squared minus 2x plus 1. Okay, and then I have to multiply by that other term. So I'm going to convert this into 4x plus 3. Because this is a factor that has a 0 of -3/4. It's not necessary. You could just bear with that fraction, distribute it, but it's easier. This. I know I'm kind of glossing over why I did that or why that's allowed. But this factor, if you set it equal to 0, I guess I'll go in a little bit. If you set this equal to 0 and convert the factor into a 0, you still will get -3/4. So just as you would for this one. So both these factors have a 0 of -3/4, but I prefer this one because for my purposes, it's easier. All right, I think I'll just skip that part. Yeah, I just got to do some bunch of busy work. But in the end, that would give you some polynomial with those zeros. Do one more of those ones. Which one should I do? see. Do this one, 43. All right, so I need to convert these zeros into factors. So I'll do this one again. I'll use the nicer version. Oops, should be plus. And if I'm a little unsure about that, I could just take the extra step and set it equal to 0 and make sure I get this as a answer. 2/3. Yeah, it comes out to the correct 0. This one's just going to be an x. And then this one's going to be x minus, and I got to be really careful with that negative. And this one, it's like imaginaries. If there's 1 0 with a radical in it, then there's going to be a second 0. That's going to be the conjugate. So that means I'll need a second factor that has that 0. So x minus again, and then inside will be -2 minus root 2. Yeah. So man, if I was doing this test, I would save these ones to last because it's kind of a long problem. All right, I'm gonna use my same shortcut on these things. Plus root 2. And then I'll parenthesize these guys, and I'll think of it as 2 conjugate binomials. So first times first is that, and then last times last is 2. So then I'll have to do it out. Plus 4 minus 2. Yuck, yuck, yuck. So boring. 2. All right, then I have to come back and do this other stuff, which is just busy work. So I guess doesn't matter which, I'll put the x in this one. Nah. Let's see. I really don't want to finish it, but I guess I'll do it. Let's see. So 3x to the 4th plus 12x squared plus 6. Oh, wait. It's supposed to be 2. Making mistakes. Let's see. 3x to the 3rd, 3x to the 4th, plus 12x to the 3rd, plus 6x squared, plus 2x to the 3rd, plus 8x squared, plus 4x. Look for some like terms. These guys, plus 14. Those guys. All right, hopefully that's right. Little likes. All right, on 46 here, so I'm going to use the calculator since I think you get that. So I already typed this in the calculator. And ooh, maybe it's not going to help me because I see it's somewhere between 1 and 2. So yeah, that's a pain. So what am I going to do? I was hoping there was like a cheater way to do it, but nope. All right. One of the things you guys learned is how to find the possible zeros. And the process is you take all the factors of this number divided by all the factors of this number. You kind of like make a big list of them. So I'll start with all the factors of this are 1 and 3 and 9. All the factors of this are just 1 and 2. So that's like a fraction. So I'm going to take each of these numbers, 1, 3, and 9, divide them by 1. So I guess I'll just give me 1, 3, and 9. And then I take those same numbers and divide them by the second possible denominator, 2. Let's see, 1 over 2, 3 over 2, and 9 over 2. And then it's plus or minus each of these. These are all the possible zeros. Plus or minus 1, plus or minus 3, and all those other ones. All right, now I'll go back and look at my calculator. And I can see it's not any of these because it's not going through the x-axis at 1 or 3 or 9. It's going through some fraction. It's not 1/2, I can tell from looking at it. It's not a negative anything. Some positive number between 1 and 2. So it's looking like this guy right here, positive 3/2. So now what I have to do is divide this out of this thing. So it goes like this. I could use synthetic or long division. If I use synthetic, I have to do 3/2. Just going to force me to use fractions. Not excited. All right, bring down the 2, multiply. So I get 3, that's nice. Double check, and then add. And then multiply, oh, that's pretty nice. And then 6, and then multiply, even that's nice. And then I get 9, and I should get a 0. If I don't get 0, then that means this was not a 0. All right, so now I get, let's see, 2x squared plus 6. And now I just have to find the zeros of this thing, which are, let's see, x squared equals -3. So that means x equals plus or minus √3 with the I. So, oh, cool, that's it. Those are the zeros. X equals 3/2 and plus or minus that. All right, so I'm going to try and use the same method for this one. I'm going to punch it in the calculator, graph it up. Oops, wrong button. Graph it up. Ooh, I see, looks like the same thing. All right, so yeah, they're making it hard for me. There's no integer zeros. So do the same thing again, write out that list. So let's see, 1, 2, 3, 4, 6, and 12 all over 1 and 2. Let's see, so I get 1, 2, 3, 4, 6, 12, and then I get 1/2, 2/2, which I already have is 1, 3/2, 4/2, which is 2, I already have that, 6/2, I already have that one, 12, I already got that one also. That's plus or minus each of these. Look at my graph, it's -3/2. Hope this one goes as smoothly. 2, 3, make sure I'm not missing any. 3, 2, 1, constant. Okay. Okay, it's going easy again. So it's the 2 and the 8 turn to 4, so it's -12. Of course, this should turn to 0. Well, it's very similar. 2x squared plus 8. So it's my answer, and I need to look for the zeros of that. So it's x squared equals -4, which means x equals plus or minus 2i. So that's it. Yeah, my zeros are -3/2 and plus or minus 2i. All right, back to rational functions. Intercepts, horizontal asymptotes. All right, sometimes it's one big fraction, sometimes they're broken up like this. If you're less comfortable with this version, you could add these two together with a common denominator like this. So you have to multiply this one top and bottom by x plus 1. X plus 1 over x plus 1. And then you could add those together to -x plus 2. And then if you're comfortable with this, let's see, there's no holes because you can't factor it and cancel. Horizontal asymptote is going to be at -1. Let's write that. Vertical asymptote at x equals -1. To find the x-intercept, you plug in y equals 0. So multiply, so you get, right, you multiply the denominator up, so then you get equals 0, and then you get x equals 2. So 2 comma 0 is your x-intercept. To find the y-intercept, you plug in x equals 0. So let's rewrite this thing. So I plug in 0 there and there, I get what, I was almost going to say -2, but no, it's just +2. So 0 comma 2. And let's see, my horizontal asymptote was at y equals -1. My vertical was at x equals -1. And from these 2 points, I know the graph's going to look like that. And I guess if it's a test, I know it's going to be something like that. But if it's a test, maybe I'll plug in like -3 into the function and just see exactly what point it gives me. Let's see. And I could use either version. It should be the same function. I think just for fun, I'll use the original function. So I'll plug in -3. So I get 3 over -2. It's kind of sucky. That's 1. So -5 halves, so just -2.5. So yeah, good enough for me. I'll just graph it. Oh, and I forgot, you could just use your calculator. In this version, I don't know if you guys use this, but this will be the horizontal asymptote. So this one, -2, will be the horizontal asymptote, which is the same thing we got. So based on that, this is going to be the horizontal asymptote. And vertical asymptote at 1. And then the x-intercept, you plug in y equals 0. The x-intercept, you plug in y equals 0. So move the -2. Oops. With cross multiplier, just multiply it by the denominator. So let's see, x equals 3 right there. And then to get the y-intercept, you plug in 0 for x. So let's see, I got +4 plus 2 is 6. I guess that's enough to make the graph. I mean, more complicated, but this one I have to start by factoring top and bottom. Math. Maybe some kind of 4 and 1. This one's a GCF. Like plot x. Careful. I'm gonna trust myself, so I'm gonna multiply this back through and just make sure it gets me back where I started. Looks good. I think it's all right. Okay. So yeah, I got a hole there. So I'll just make a little note. Hole at x equals -4. And to get the y coordinate, I have to plug -4 back into what's left over. So let's see, I got -3 on the top and 8 on the bottom. All right. Let me get that other stuff. So let's see, horizontal asymptote. It's just the ratio of the leading coefficients if they have the same degree. Of course, if this was 3, then it won't have a horizontal asymptote. Just keep going straight up or straight down. But if the bottom is bigger, then the horizontal asymptote is 0. Oh, and of course, again, you could just plug this in your calculator. The calculator is not going to show you the whole, but you should be able to figure out some of the other stuff just from looking at the graph of this on your calculator. Oh, let me turn that. Oh man, I guess that I should hope that the calculator is probably in the way for those last bunch of problems. Let's see. Go back and you could screenshot that and look at it later, I guess, or just pause and go back to 51. Was it in the way for these other ones? Dang it. Dang. I don't know how long that calculator was in the way there. Probably a long time. All right, all set. All right, vertical asymptote at x equals 0 based on that. And then I guess I should go back and get the x and y intercepts. We were just saying, yeah, you could just plug this in your calculator and get the graph. For x-intercepts, you plug in y equals 0. So basically, whatever's in the denominator is going to get multiplied up into the 0. And the top, I'll leave it in this factor form. So I'm debating whether I should keep the x minus 4, but I shouldn't because it was a whole, so I'll eliminate that. So my x-intercept is to be -1. Yeah, it's careful. I almost left the x minus 4 up there, which would have given me these 2 x-intercepts, but I gotta ignore that one because it was the whole. So the y-intercept, plug in x equals 0. I'm going to, again, use my my simplified version of the equation. Let's make it easy, I guess. And I can see I'm going to get a divide by 0. So looks like it's not going to have an x-intercept. All right, horizontal. I should just push in the calculator. X-intercept -1. And I guess that's it. And then to graph this one accurate, I mean, do I put it like that? Should I put it like that? Somewhere in between. Probably should just plot 1 point. So maybe I'll plug in 1 for this and see what I get. So I get 2 over -2. I get 1. So 1, 1 should be right there. Try and knock out a couple more. I'm jumping up to 55. More yucky math. So let's see. I need a. Looks like they almost all have a common denominator. I guess I should factor. I can see that's b times b plus 2. So I just have to multiply this one by b over b. And then they'll all have common denominators. And once they have all common denominators, I can just delete them all. When it's 5 equals 2 plus 3b. I'm home free. All right. So this one, I just have to multiply the 1 by 3b minus 4 over 3b minus 4. So let's do that in my head. Because it's just 3b minus 4. And then once all these denominators are the same, I can just cross them all out. Okay, subtract b from both sides. I got -3 here, which I'll add to both sides. So b equals 1/2. Oh yeah, and I forgot, look for extraneous solutions. So when I get b equals 1, I should make sure that's not like a domain restriction. Meaning I should make sure that's not like a 0 of one of the denominators, but no. So the numbers that's not allowed to be a solution are equals -2, that's not allowed to be a solution, and also 0 is not allowed. So if this had come out to 0 or -2, I would have to cross it out and say extraneous. So let me check 1/2. No, 1/2 is okay, so it's not extraneous. I'm just gonna do one more, I think, for today. Solve the inequality with. So for me, I guess there's a couple ways to do this. You graph it, but I'm just gonna use pretend it's an equation. And then solve, so you get x equals 6 and -5. And then you do a number line. And these are going to be open dots because it's greater than. I've got these 3 regions to test. So I'll test a number from this region. I'll plug in -100. Let's see, I get -106 times negative something. So negative times negative is positive, which is greater than 0. So that's a winner. So this whole region is a solution. Number from this region, 0. I'll plug in 0. -6 times 5 is -30, which is not greater than 0. So that's not going to be the solution set. I'll plug in 100, so I'll get positive times positive. So my solution set for this one is -infinity all the way up to 5, open bracket, union, 6 to infinity.